Hello, good morning, good afternoon, good evening, everyone. My name is Kelly Lyons, and I'm a professor in the Faculty of Information at the University of Toronto with a cross appointment to the Department of Computer Science. I'm currently serving as Acting Vice Dean Research and Program Innovation at the University of Toronto School of Graduate Studies, and I am a faculty affiliate at the Schwartz Reisman Institute for Technology and Society. Welcome to the fifth session of the Women in AI series, a collaboration between the Schwartz Reisman Institute and Deloitte. The purpose of this series is to convene leading female researchers to share knowledge and mentorship opportunities for women across the technology sector, with a particular focus on artificial intelligence. Participants will explore the development of new technologies and approaches and insights into cutting-edge research from the perspective of our esteemed guest speakers. To begin today, we want to take a moment to acknowledge the land on which the University of Toronto operates. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. These and other Indigenous peoples across Turtle Island developed complex and effective governance systems based on respect for all life and the intelligence of the natural world. Today, this land is still home to many Indigenous people working to reclaim their rights to self-governance, and we are grateful to have the opportunity to live and work on this land. Although we may be all joining from different places, we encourage you to reflect on the history and relations of the land that you are on today. Before we move into today's talk, I'd like to introduce our collaborator in this series, Aisha Green. Aisha is a senior manager at Deloitte's AI Institute focused on AI literacy and adoption. She is passionate about fostering partnerships which advance research and innovation initiatives, and has worked closely with early stage entrepreneurs to commercialize medical devices, therapeutics, and information technology applications. Welcome, Aisha.
Thank you, Kelly, for that warm introduction, and welcome everybody to this fifth lecture that we have through this initiative. Over the past few months, AI-enabled language models have expanded how we interact with our world, derived new content, and forced us to consider how knowledge is shared. Despite all the excitement, there are still guardrails to consider as we explore the endless possibilities of AI-enabled tools and applications. For today's lecture, we asked the question, what if we could increase the speed and reliability of knowledge discovery using natural language processing? From our esteemed researcher today, we will explore how text mining, natural language processing can facilitate the discovery of new knowledge, how semantic search of biomedical literature can quickly review safety and health incidence reports in construction industry, and also potentially identify risk. We'll also hear what it means to be a woman within this space and how our speaker has navigated her career path to ensure that her work has a broader impact on the world in which we live. We hope that the conversations you hear and the networks that you start to begin and foster throughout this series will fuel change that is vital for this sector for both women and allies. With that, I turn it back to you, Kelly, to introduce our lecture for today's session.
Thank you, Aisha. Very quick few notes before we begin. The session is being recorded. Our guest will speak for about 45 minutes to an hour, and we'll take questions after the talk. During the Q&A, we encourage participants to use the raise hand function in the Zoom meeting controls to ask a question. I will call on you. And please invite you to update your display name with your first and last name so it's easier for me to reach out to you when it's your turn to ask the question. And now I'm very pleased to introduce our speaker. Sophia Ananiadou is a professor of computer science at the University of Manchester, whose main research areas are natural language processing and text mining applied in biomedicine. She is the director of the UK National Centre for Text Mining, deputy director of the Institute of Data Science and AI, and Turing Fellow, an Ellis member, and a distinguished research fellow at the AI Research Centre. Sophia's research interests are based in how AI systems can acquire and exploit language, particularly in specialized domains. She has played a leading role in bridging text mining with systems biology, bioinformatics, public health, as well as in the humanities and law. Without further ado, Sophia, the floor is yours.
Thank you. Thank you very much for inviting me. Let me share my screen. So I hope everybody can see that. Thank you very much for the introduction and for the invitation. It's really a pleasure and an honor to give this talk to this audience. And I hope it's going to be quite very inspiring for not only for women, but for several other researchers. As you heard in the introduction, I'm a researcher in natural language processing, and most of my work has been done to apply to biomedicine and health. So my talk here is going to be the outline about information extraction, specifically from biomedical text. And I'll focus more on name entity recognition and two different types of name entity recognition. One using neural networks, but also span-based NER. And then work on relation extraction. And then I'll focus a lot on pre-trained language models, specifically their role in biomedicine. And most of the time I'll talk about summarization methods and several applications. So a bit of introduction about the center that I'm responsible of since 2004. We're working on natural language processing and deep learning, although in the past we're working mostly on machine learning and deep learning. Our work was to focus on the development of tools, of different resources, but also NLP infrastructure to assist fundamentally translational research. So I applied most of my work in biology and medicine and health, but also engineering and law. So the methods are quite generic, but also applicable in different domains. So we work on knowledge discovery, but also curation of pathways and databases. We constructed different search systems, semantically based search systems. So a lot of focus on the systematic review development for public health. And the rest on methods was on information extraction, text summarization, text simplification, and emotion detection, in particular for mental health. Last but not least, all this work requires the development of different resources. By resources are also training data, annotated data, and terminologies, and also dictionaries. So all the work that I'm going to present today, it's open, and you can find it on our website, which is thenactem.ac.uk. So I'll start with name entities first, which is for people who don't know NLP. In information extraction, we have three main parts. First of all, is the information retrieval, but in information extraction, typically we will extracting name entities, relations, and also events. And I'm not going to talk about the last one today. So to give you an example of what is name entity recognition, if you look at this sentence, you see the first one is a chemical compound, and the alpha AR, it's a protein. So those are what we call name entities. So they are a group of, or a word or a group of words that constitute a proper name. Typically, they have what we call a semantic hat. In this case, we have a chemical or a protein. And importantly, they have a span. And I'm talking about span because I will discuss about spans in the second part of my NER. So those are the words like alpha AR that are included in the entity, which we need to recognize. So the input of NER is a textual snippet, and the output is a label of each token in the sentence. But typically, in most fields, in most areas, the name entities are predefined. So when we work with users, they're saying we want to extract name entities of chemicals or proteins. And typically, those systems, we need to provide training data, either for training or for validation. And there can be those name entities very fine-grained or very coarse-grained. Most NER systems have reached almost human-level performance on NER. So why they're useful? Actually, they're more useful, perhaps this first step of information extraction is the most useful element because it's important for other downstream tasks, like relation and event extraction, but also applications such as search, semantic search, or question answering, summarization, etc. And it's also important for any type of classification based on the content on the entities, or for risk analysis, etc. But named entities have also their challenging, especially in areas in specific domains like biomedicine. We have what we call lots of nested entities, which I will introduce. And also they tend to be, because they are nested, very often ambiguous. So they can belong to different categories. So a string, for instance, a span of text could belong to a protein or to something else. Also, still, it's very difficult to detect very fine-grained entity categories. And most of the time, this is because they're sparse or there is not enough, for instance, evidence about to detect those fine entities. So to explain to you what are these nested entities, they're typically, as you can see from the examples here in both sentences, they're embedded in longer entities. And typically, these entities share the same text span, but as I said before, they have different types. And very often we call them our polysemous entities, as for instance here, a narcotic-induced respiratory distress. There could be an adverse drug event, it could be reason, or interleukin-2 receptor, you have DNA and protein. So how we go about recognizing the community, the natural language processing community has spent a lot of time dealing with these entities. So here is a work of one of my ex-PhD students, Meiji Zhu, who actually provided a model architecture for a nested NER. This model was quite old now, because it's 2018, but it's one of the first ones actually working on nested NER. And is designed basically based on a sequential stack of flat, what we call them NER layers, that detect the nested entities in an end-to-end manner. So each flat NER layer consists of a single LSTM layer and a CRF layer. So if we look at the example here, mouse interleukin-2 receptor alpha gene expression, this contains two entities, protein and DNA. We first stack one flat NER layer to identify the inner entity, which is interleukin-2, which is then further used as the input to identify the outer entity, interleukin-2 receptor alpha gene expression. And the model very simply stops stacking flat NER layers when we don't detect any more entities. Now, the difference from other models here is that basically we are using the same flat NER entities. We extract entities in an inside to outside manner, and we use what we call the dependencies among the different nested entities. And also important in this work was to be independent of different external resources. This work has been applied in several areas, not only in biomedicine, but also in other techniques in engineering and law. Now, one of the important parts here is the notion of span. And a span has more than one name entity, category, and nested entities. So how do we work, how do we deal with span name entity recognition? This is very recent work, produced mostly by Nguyen, which is going to be appear at the ACL. So this work on span-based name entity recognition, there's quite a few actually people now working on that. Typically, the previous one has been, and most works on NER used sequence models, for instance, such as BIOLSTM for nestness and BERT. So at the same time, as I said, we've seen the rise of span-based models, which are quite simple and quite effective. So by using a span-based model, we can directly represent and manipulate span representations. So in this case, we've been quite inspired by the notion on information bottleneck by Tilsby, which actually compresses the representation while preserving meaningful information. So we distinguish here two methods for information bottleneck. So first is the unsupervised IB, or what we call the very well-known variational autoencoders in different NLP tasks. This includes sequence labeling or dialogue response generation, relation extraction, which we have done ourselves. And also we have then either the supervised model or variational IB, which has been used for fine-tuning low-resource tasks, machine translation, and text classification. So in this type of work, typically, most people used only one type of the information bottleneck model. So either we use the VIB or the VA in the system. So we tried to explore if we could effectively combine the two types of IB models. So the model, actually, our idea was to learn span representation is actually differently from other approaches. So we update the span representation using span reconstruction and synonym generation. We then compress it by selecting relevant features using the information bottleneck model. So let's see a bit more how it works. So as I said here, the difference is from other approaches to do span-based NER, which is important for the people who came now to the talk, important for nested name entities, is to combine the two types of IB models, either supervised or unsupervised. And we also jointly trained the span-based NER system with those two components, with two VA components and one VIB component. So the first one, as perhaps I could show it here. The first VA component is span reconstruction, used to reconstruct the original spans. And the second VA is for synonym generation. So we used to generate the synonyms of a span. We also collect those synonyms for each span from an external knowledge base. Here we used UMLS, but obviously the method can be used for any kind of knowledge domain and knowledge base. And then we train a VA model that can generate the corresponding synonyms given a specific span. By now, the important part here, and you will see it later on when I talk about summarization, is how we inject semantic information into our models. And we do that by using basically the synonym generation, using the knowledge base, and indirectly inject semantic information from synonyms into the span representation. And the last part here is the VAB component, which is introduced into the system to compress the span representations while actually keeping useful features for the NER. So this is the basic model of the basic representation of the model. So let's talk a bit about the experimental results. Here, there are lots of other informations which I've decided to omit here because you can read the paper. We experimented with different data sets They're all biomedical, but as I mentioned, the method could be used for other techniques as well. So we have the NCBI disease data set, the NC5CDR. This is in biocreative. This is divided into the disease and chemical. Share and Clef, the Genia corpus, and the med mention, which is a large biomedical corpus annotated with UMLS concepts. The encoder, in this case, we used the Cybert, and for the synonym detection, we used exact matching on UMLS. So the word vectors to the decoder were vectors trained on PubMed and PMC text in English Wikipedia. And the baseline we used for that was a span-based NER, which we have introduced before in the Deep Event Mine. So this is mostly inspired by Zohrab and Miwa about span-based work. So as we see here the results, we see that by using the joint model, we have improvement in most of the corpora that we have used based on the baseline. So to summarize that joint, of course, there is a lot of work to be done, but this is the first study that investigated the impact of combining a quite well-known concept of information bottleneck into NER by not using one method, by combining two. So the span reconstructions keeps the contextualized span information, the synonym generation indirectly injects semantic information into the span synonym, and the VIB NER preserves the information about the target NER while filtering out irrelevant information from the input. So there is a lot, of course, of we demonstrated this is a promising work that we would like to explore a bit more, because it's the first time we're using a joint model, which improved for a span base, especially for nested NER in most cases. And in-depth analysis also indicate that each component, the span reconstruction and the synonym generation and the VIB NER, played a different role in enhancing the span representation. So this is the first part of the NER, and I would like to give you kind of a small, stop on the technical part to discuss how we can use NER for semantic search. For this type of NER, we use the more traditional techniques, but for people who don't know what the NER can do in a real-time application, I thought it would be important to demonstrate. So this is something we have done some time ago, and we used, this is our system Thalia, which actually does a semantic search based on name entities. So we use the abstracts, the whole of PubMed. You can find it on our website as well. And the types of entities we used were predefined, as is typically the case in NER. So we used chemicals, diseases, drugs, metabolites, because we're working a lot on systems biology, but also anatomical entities and so on. So those are name entities which actually can be used for all sorts of applications. In this case, you see things like unnecessary workload. We used it to support search and systematic reviews. And one of the challenges that people have that is to balance the information, having to filter, having to screen too many documents. And by using this type of system, we can actually avoid to have an unnecessary workload by providing a very simple, just a simple keyword query. So an example of that is CAT, which could mean really anything from an acronym to, to a real word. So if you do that in PubMed, you will retrieve much more abstracts than you retrieve now. So obviously for somebody, a researcher has to go through all those abstracts and find out which ones they have to include. But by using name entities, we can do what we call faceted search. And by specifying the semantic category of the query terms, we can reduce the number of papers by almost 85%. So for instance, we might be interested in CAT as a protein. And typically, we link these types of entities with databases or existing resources, in this case, with UniProt. And also typically, those entities, they're linked to various databases because they can be also ambiguous, and we can specify which ones we want to use, to include. Another example here is GAD. And we have to remember that in biomedicine, very often we have many acronyms. Although we have developed other systems that identify and disambiguate acronyms, in this case, which I won't explain in this talk, they're also in the back end of this system. So we are also performing acronym recognition and disambiguation to allow us actually to expand the acronyms in our search. Also by doing acronym recognition and disambiguation, we can improve name entity recognition. So here GAD could be generalized anxiety disorder, but also it could be a gene. So it's up to basically we can decide by disambiguating the acronym to reduce even further the number of articles that we have to 1,600. So we can see there how we can balance the specificity and the sensitivity in search by disambiguating acronyms. So this is a very simple example of what NER can do. But now I'll go to another step, which is relation extraction. So again, this is a very well-known area in natural language processing and has it could be very useful for several applications. So in this case, we have identification of patterns from raw text. So injury disrupts physiological function. So you have, for instance, patterns like pharmacological substance causes pathological function, etc. So relations are important for the development of knowledge graphs, of knowledge bases, and also important for subsequent tasks. It could be for question answering systems, for event extraction, and also for different automatic identification of complex of different biomedical and not only associations. So they're really an important task for several applications. So let's see a bit some of the challenges that they have. So obviously there are several. We see the different aliases. There is coreference, polysemy, which I'll describe very briefly. But also all those are linguistic phenomena that are happen because of the diversity of language. And also we have several other grammatical phenomena or modality in relation extraction, such as, for instance, negation or certainty, uncertainty, etc. I won't discuss about these aspects today, although we have worked on that. And also there are semantic challenges, such as implicit statements or common sense knowledge, etc. So for the main aliases, especially in the biomedical domain, we use techniques such as name entity linking. I mean, you saw before in the semantic search system I presented, you have a name entity, and typically we link it to different databases. We call it like normalization. But also we can use hierarchies between different entities, and different ontologies can also help us to do these associations. So for ISA or other types part of relationships, such as like ISA and hypernym, and other types of work that we have to identify are negation. So we have here neither nor or blocked. So there are different ways of, it's not always negation, it's not always presented with no, but with different expressions. And if we want to extract relationships between entities, we need to know if a relation is, for instance, valid or if it's negated. And last also is very often in text that we have arguments which are quite distant, as you can see here in this example. You have bilateral optic neuropathy, but then you have a whole parenthetical sentence, relative close, and then you have also isonia Z. So those are challenges of relation extraction. And also, last but not least, is the implicitness of relations, which are mainly due because text could be, for instance, in electronic health records, we have very telegraphic text, and we need to be able to assume, to infer relationships between different entities. And again, I'm not mentioning temporality, but all those aspects are extremely important in relation extraction. So I'll talk a bit more now about the specific case study, which is about the medication-drug associations, which is the work of my ex-PhD student, Fenia Christopoulou. So again, the challenge that we had at the time is that in relation extraction, most of the work that had model interactions between pairs in a sentence. And they assumed really that we have a single pair per sentence. Very often as well, they depended on external syntactic tools that resulted in very domain-specific models. So the motivation of this work is that, as I said, some relations are not explicit in text, and we need to be able to infer them. But also they might not be, if we're using supervised techniques such as these ones, they might not be annotated, but we are able to identify them by inferring these types of relationships. So the hypothesis is that if we have a relation between an entity pair, this can be supported by coexisting pairs in the same sentences. Sorry, let's do that. So this is an example of what I'm talking about. We find the relation between hypotension and atropine. So, and in this case, we also, this type of, because it's quite far away, this type of relation is not evident when we first read the sentence. So, but if we use additional intermediate associations between hypotension and dopamine, and which is with the evidence like wind down, and also dopamine and atropine with the evidence required, we can then infer the relation between hypotension and atropine. This is, as I said, very important when we don't have enough contextual words in the sentence, but we have multiple name entities. So in this case, we can use additional drug-drug interactions although they are this, for instance, in this specific case, they were not annotated in the corpus. This was actually work we have done as part of our participation in a shared task, then N2C2. So the method is really as follows. Oh, sorry about that. So it's actually a mapping a sentence into a graph structure where the nodes are the entities in the sentence and the edges are representations of relations in the same sentence. So the model which we have developed we call a walk-based model on entity graphs. And so after we construct the edges, our model, we aim to model basically chains of interactions between the target entities. So the walk-based model has a two-step process. The first one is the walk generation. During the walk generation, we combine two direct representations into a direct one. So hypotension and dopamine and atropine. And then during the walk aggregation, we combine, it's here, sorry, we combine the old, which is the red direct representation, with the new, which is the yellow indirect representation, into a single new representation, which is the blue. It's updated. So the edges are updated using both direct and indirect representations. So so far, we looked, this is a really supervised method based on sentence-based. So we look at relations which exist in the same sentence. But however, we can have also relations between entities in different sentences. And that's, again, a very challenging task. So the two types of relations, one is an entity relation. So you can see here, oxytocin or ox is a deuterotonic, and then it can cause significant hypotension. And the second one is a concept-based, where actually you have multiple mentions and we unite them into one, oxytocin. So we have either entity-based or concept-based representation. The first scenario, we consider the occurrences of each entity as a different name entity. And in the second scenario, we consider them, all these multiple occurrences of an entity, as mentions of a particular concept. So in order to learn from multiple occurrences of the same concept, we use the techniques like multi-instance learning. And the goal is to determine the relation of a pair based on the instances of this pair. So this just to explain a bit more how it works in a document. So this is relation, basically extraction on a document level. And those are the examples of what we call intra and inter-sentence associations. And some observations we can have here is that the inter-sentence associations also require some logical reasoning and inferencing, which we're trying to do. And sometimes entities can occur rarely in the document, like, for instance, scotoma. But some sentences also, they're not informative at all for the association we aim to find. For instance, the same sentence number 2 is, for instance, not so informative for the association of ephantopol and scotoma. So to go as first step of the same model, of course, there are several other models that we have used since then. For inference, we can use the walk-based mechanism, which I briefly mentioned before. But in this case now, a big difference is that in the graph is that we have a heterogeneous graph with different types of nodes and edges. So I talked about entities and mentions and sentences, and the different and multiple types of edges between mentions, entities, etc., and sentences, direct and indirect. So the model, the inference mechanism is the walk-based model. And then the model can create and update new paths between the nodes and update existing paths. So as we can see here, we can create, for instance, a representation for the path between the yellow node and the brown nodes. So to see a bit the experiment evaluation, we have done it for a distance supervised corpus, which I skipped here. This is on the CDR data set, which is a chemical disease interaction data set. It's humanly annotated and contains about 1,000 abstracts with 30% intersentence. So we compared our model with state-of-the-art approaches, which are again independent, and that's the difference of external tools or use additional tools and data. So there are three different types of additional baselines. The EOG is the proposed model, the edge-oriented graph, but also there's the fully connected graph, or when we discard the walk-based model, or when we trained only on sentences. And very briefly, because I don't want to spend all my time there, we can see that the document, first of all, level associations are important for the sentence base in both data sets, if you look at the EOG versus the sentence. Also, the model is independent of any syntactic and dependency tools, and can still achieve state-of-the-art on a manually annotated and document level chemical disease data set. So the intersentence associations, they can be also beneficial for the detection of the intrasentence. So to summarize, this is an edge-oriented graph neural model for document level, relation extraction, and it consists basically of a graph of heterogeneous types of nodes and edges, which models both sentence-based and document intra and inter-sentence pairs simultaneously. So now I'm going to the last part of my talk, because this is a very interesting part for other applications that we have developed. And mostly, if I have the time, it's about how we could improve the synthesis part summarization in systematic reviews. This is one a type of application we have worked a lot in our center. So first of all, what is summarization? Well, it's really, you have a set of documents and you have, just speed up a bit. Okay, so basically text summarization is the task of converting a longer piece of text into a shorter piece of text, while obviously communicating the same key points from the original document, and that's quite important. And the value of summarization is mostly derived from how the efficiency, the time we gain through distilling long documents into shorter text. Now, despite all that, because we're talking about longer documents and shorter text, most studies which research on text summarization have primarily been based on short documents, and I'll explain the difficulties with that. And here is the time now to introduce the pre-trained language models that everybody's talking about. So pre-trained language models, we all know, we have been used to improve the performance of text summarization. This self-supervised pre-training makes the PLMs, which I'll talk in pre-trained language models, to memorize common sense and also lexical knowledge, which is inherited in the training text. And this can then be transferred to improve different NLP tasks in summarization, for instance, like fine-tuning. Now, we have two types of summarization. We have extractive and abstractive. Extractive methods really select key sentences from the original documents and amend them, concatenate them to produce a summary. And abstractive methods generate new sentences. Now, if we comparing abstractive to extractive summarization, abstractive is much more challenging. And one of the difficulties as well is for abstractive summarization methods is to generate factually consistent summaries. And factuality is something I'll talk again. And this factuality is something that people talk a lot recently, especially with ChatGPT. So it's actually how it involves how we can have informative sentences from a large vocabulary and for basically of different domains as well. Now, the difficulties with PLMs is that they're limited by the need of large corpora of data for pre-training. Ideally, we want to do them, as we will see, in the domain of application, for instance, biomedicine or law, etc. So the lack of the label training data for fine-tuning and also for their attention mechanism, which also makes them not suitable for long documents. And that's an issue. Summarization, you take a long document and you try to make it short. Because this is a kind of computational complexity of the attention mechanisms, it means that if you have a long document, you have to truncate it to be computationally feasible to process. But if you truncate it, you lose information. So we try now to examine methods to adapt the pre-trained language models to make them more suitable for summarizing long documents. So this is again an example, which I think more or less I've said before. So I don't need to repeat. And this is something that to emphasize here is the, how we can produce factually consistent summaries. And don't think I'll have the time to talk about that, but now this is about the factually consistent. It's important to, it's related with the types of evaluation metrics that we use to assess the efficacy of these methods. Because most of the evaluation techniques, they're looking at word overlap and they don't correlate well with other important measures, such as, for instance, factual consistency. So this is an area of research, how we can improve the metrics for text summarization to deal with factuality. So a very brief overview of PLMs, pre-trained language models for summarization. And again, they have a similar framework to neural methods for both extractive and abstractive tasks, but they're more powerful than neural networks in encoding biomedical text. And early language models use BiLSTM, for instance, ELMO, as the backbone network structure to capture the bidirectional contextual information of text. Now, transformers are able to model long-range dependencies of sequences. And basically, most of the pre-trained language models use transformers. So pre-training, again, on a large scale of unlabeled data is it's key for language models to learn representations and different parameters, which then can be fine-tuned to different downstream tasks. But there are two issues here, because we're talking about biomedicine or any domain specificity. Most advanced pre-trained language models, such as BERT, GPT-3, etc., and T5, they're pre-trained on texts of the general domain, so like book corpus or Wikipedia. And it's very challenging, as we all know, to apply these models to biomedical texts. one of the major issues is that we use terminologies or compound words in biomedicine. Most of those have not been mentioned in the general language, or if they're mentioned, they mean something else. These elements are very important to be embedded as salient information, which is fundamental in understanding biomedical text. So to fill this gap, obviously, people have used a lot, have developed methods like BioBERT, Clinical BERT, PubMed BERT, SciBERT, etc. There are a whole variation of BERTs especially for the biomedical domain, but this is happening in other areas as well. For instance, legal BERT. But that's extremely fundamental, and we show why this improves the performance. Some of for biomedical, for single, very well-known data sets I mentioned this before, is PubMed, is the most commonly used data set, and it's used as a benchmark and is also widely evaluated by the general text summarization methods. There is CORD19, there is the CDSR is for Cochrane, which supports the task of an important part of lay language summarization. I wouldn't have much time to talk about this today, but just as a parenthesis here, there is a lot of work of simplification, which is quite related with the summarization, how a summary could be used for different aspects and for different levels of people. So if you have an expert, you would have a different type of summarization than, for instance, the general audience. And that's, again, having to do how we evaluate our summarization systems. So now I mentioned about the limitations of the PLMs. And I mentioned about one limitation is the lack of the need to have labeled training data, and also their attention mechanism that makes them not unsuitable for long documents. So this is the work of my MPhil student, Jamie Bishop, who has produced a very nice work, or compare some. And this is a hybrid unsupervised summarization method using salience. So it's an abstractive, extractive method, which actually cycles through a document, and generates salient textual fragments, and uses this to guide an unsupervised extractive summarization. Now, the hybrid approach can be easily extended to any document length, and experiments we have done shows it outperformed existing unsupervised methods and also state-of-the-art supervised, despite the fact of not needing label training data for the summarization part. So let's see very briefly how this works. I'm not going through all the details, but to sum up, the method is comprised by two basically steps. First, using a generative model, it could be any of them, like T5 here, you generate the salient textual fragments. And these are basically, could be queries or document titles. Now, this represent key points from across a document. And then you do a comparison between these salient fragments and each sentence. And you select the most important sentences from across the documents. There are various details about that, how we select the similarity between a sentence in the original document to the selected salient fragment. We use BERT score, but this I will leave to people to just go through the details of the paper. So it's basically a very simple two-step process. So the results of that, we used a well-known data sets, PubMed, Archive, Stork, CORD19 data sets, and also experimenting with different extractive text summarization methods. which are compared. And in this case, because we're looking at long documents and short documents, we compare both short and full text versions of the 4 scientific data sets. And the reason we did that is because in all the related literature using transformers, they either evaluate them on short or truncated text. So we need to create short data sets for evaluating our models. Then we basically implemented Gen compare sum and compare the performance between those different generative models, doc-TTT query, T5 med query, etc. Now, for the long documents, as we can see here, Gen compare sum with T towards T5 stork title outperforms on other unsupervised models and also outperforms LexRun. So what is actually the important part of that, because too many details, if you're interested, you can read, is an unsupervised technique which can be expanded to any length of document. It does not require a corpus of annotated training data for the extractive summarization task, and also outperforms strong supervised and unsupervised baseline on long and short documents. Now, because the model uses the title and document pairs for the generative task, which is the key there, these are readily available across many domains without the need to have a manual labeling effort. So this is one way of overcoming some of the challenges of PLMs about first of all, the long documents and also the availability of training data. So obviously there would be, there is a lot of work on that, is to, more on the human evaluation. And also we have done some work on different metrics, which I'm not discussing here. But another obviously interesting part, aspect is to look at other parts of the document. For instance, we can include zoning into the method. And also besides T5, we can use different like BART-based models or models trained with different data. So there is a lot. This is a kind of first work by her, but there could be lots of other experimentation. So we're talking about long-range dependencies. This is another of the challenges of pre-trained language models, is to capture long-range dependencies. And this is, again, for summarization, one idea to address this shortcoming is to use neural topic models. And this actually have been incorporated before into PLMs to improve text summarization. And the reason these are important is because they can provide more the topic models, what we call the global semantics, the latent topics. But there is a problem with that because most models, they do not consider information from the gold summary. So you have a long document and then you have an abstract is the gold summary. And then you have to consider also the full contents of the long documents when you're learning the topics. So sometimes that creates a kind of wrong assignment of the document because your topics might be suboptimal. So you extract, for instance, sentences that they have high frequency words, which is not necessarily important, and they have very low similarity with the gold summary. So one way of doing that, and this is the work by Tian Xie, it's a postdoc in my lab, is to address it, is basically to propose a graph contrastic topic enhanced language model. This is called Gretel. And this model incorporates the graph contrastic topic model with PLMs for long document extractive summarization. So, the graph contrastive topic model, the first distinguished feature of Gretel is how we use the hierarchical transformer encoder to fully embed the global context of long documents. And then that informs the topic representations of the documents and sentences. Then by using the graph contrastive learning with the supervised information from the long summary allows the model to select better key sentences, which are actually similar or topically similar to the gold standard. So basically, by doing that, you have a better, you can distinguish more effectively salient sentences from documents by using both global and local semantics. The experiments there are again using the well-known data sets. We have, for instance, experiments on 4 benchmark data sets and 2 biomedical domain-specific data sets. Again, PubMed long and PubMed short. And it's again the same idea that I said before about truncating documents, etc. The model has been compared with state-of-the-art extractive summarization methods, which you see here, including PLM-based methods, BERT-SUM and MATSUM, and PLM-based methods for long documents, which are the second part, and then topic graph SUM, which is a topic-enhanced transformer method. So this is actually the only PLM-based model with topic modeling for extractive summarization. And the results, I don't know, maybe just to summarize, typically we evaluate summarization using Rouge results. And again, there are different types of Rouge here, 1 gram, 2 grams, and long LRL, Rouge longest common subsequence. Subsequent, sorry. The methods actually shows that it performs better than other baselines, mainly because you just you capture the global semantics using the gold summary and the full contents of the documents. And also another thing, when comparing with topic graph SUM, by incorporating latent topics, you have better performance on all data sets, because again shows that the benefit of the supervision from the gold summary and the integration of contextual representations to have a better global semantics. This is actually, to summarize, you see that how you can address some of the shortcomings of PLMs for summarizations. So just to summarize on that, you have, you can provide PLMs with neural topic inference to fully incorporate both local and global semantics. And experimental results also on both general and biomedical data sets show that our model performs quite well in state-of-the-art. Now, this framework has been used for other approaches that we have done, and this is using citation and where summarization. So now I'm not so sure how I'm doing with time. I hope I'm doing okay. You can.
We're just about ready for discussion period. So
okay, right. So I'm going to just very briefly say a couple of more things, and then we have the discussion. So obviously I didn't have the time to say all the things I want to say, but it's very important to mention that in biomedicine, one other type of work is to incorporate, to inject medical knowledge into PLMs. And again, if you directly fine-tune PLMs, you cannot capture the medical knowledge. So I mentioned this before. You have domain knowledge, you have entities, specialized terms, which are not considered. And this is another work of injecting directly the medical knowledge. This is a PICO framework, but basically by using a knowledge-enriched PLM, by creating knowledge-enriched PLM, you can improve the performance. I don't have much time to say anything about that, but I will just say briefly that this has been achieved by using what we call knowledge adapters to be able to improve, but basically to use both generative and discriminative training. And I will just briefly on that, I just don't want the results. But another part, which is then I'll stop, is using citations for biomedical summarization. And the reason we're doing that is because there are connections between the scientific papers. And we have seen that by using citation graphs are quite important for generating the summaries, and specifically the cited text spans. So I think I would stop there. I wanted to say more things, but I don't have the time. But I will ask, people ask me questions and I can perhaps respond to different questions. So thank you. I'll stop sharing.
Thank you so much, Sophia. That was really great. There's so much you're doing and not enough time for us to learn about all of it.
This is work of my team. Oh, well, actually, sorry. I wanted to put the names. I have the names, but I'll put them in the end because I want to credit them for the work they've been doing.
For sure.
So yeah, that's basically I'm happy to take any questions.
Great. We have a couple from Aisha in the chat, but I'm going to take the moderator's prerogative to ask a question. So when you're working across disciplines like this, what role does collaboration with other groups and other organizations play, and how do you manage those collaborations?
That's a super important question. Thank you for asking it. That is specifically if you're working in domain-specific areas. Well, there are two parts. The first is our discipline per se. Even if we work on generic data, so general language, the domain, the area of natural language processing is not anymore computational linguistics, obviously. So we have machine learning, we have deep learning, we have all sorts of other disciplines which are interconnected. And I always found the collaboration with teams that they have different perspectives. It's extremely important. So very often novelty and innovation comes from people coming with different hats and thinking out of the box. There is a danger in any field to keep on trying to improve performance in a kind of very narrow way. And we don't see other perspectives, and we also don't see in the past how other people have addressed. That's one thing. The other answer to that is when we are dealing, because I work a lot with the clinical data, biomedicine and law, is the integration and the work with domain experts. So I didn't have the time to talk about the work we are doing currently with summarization about evaluation. And if I may, I would like to use your question to say some of the things I didn't have the time to do. So one of the important parts for us is the human evaluation. And I mentioned about factuality and how we can evaluate systems, not just in measures, in metrics that are automated, for instance, strings and how the precision and recall. And for this, especially for biomedicine, we need to engage a lot with users and domain experts. So without some people call that the human in the loop, the different types of perspectives. So without having this feedback, it's quite difficult to produce systems which are actually useful for several applications. So I think that's very important. And how I engage, just to give you an example, we now started working actually with a university in Canada who are working on evidence-based medicine. And we very much hope they will help us to evaluate some of our summarization methods for PICO, which is population intervention outcomes and comparator. So these are really the types of information we work together. We provide summarization tools that help us to improve them by having, first of all, developing data sets and providing evaluations for us to improve our models. It's absolutely a must. We wouldn't be able to do those things without having domain experts.
Yeah, it's always important to engage with the experts of the domain when doing
especially in biomedicine, because we talk a lot about interpretability as well of our models. And in deep learning, we all know there is a black box. So how we can, for instance, know about the results if they're factual. And this is one of the issues with the ChatGPT right now. People are talking about errors or about hallucinations and about producing non-factual results. So again, we are correcting ChatGPT, and our users are correcting our systems.
That's great. I was going to ask you about that too, but I'm going to send the floor over to Aisha to ask her questions. And
sure, and I think, Sophia, you sort of touched on one of those questions that I was trying to get at, sort of the abstraction model and looking at the factuality of it. So you're absolutely right. I think that's where everyone's gravitating with generative AI. How do you model, or how do you improve or refine these models so that they are factual? And I think you've slightly touched on it on putting humans in the loop, but would love to hear how you expand on that and what other things people should consider.
Yeah, I mean, in our case, it's the factual correctness, obviously, of if we take summarization, is very important for several applications. So in our case, we also have, first of all, I didn't have the time to talk. We are also devising different metrics to evaluate for instance, summarization. This is very much inspired by the specificities of a specific domain. So, we have, for instance, in biomedicine or in law, we have what is important is technical terms. These are basically the concepts that determine, a domain, that what is salient in an area. So, so it's important, for instance, to think about, with the humans in the loop as well, to evaluate the factuality of the results based on devising new metrics that we typically use. So currently, if I took summarization, people, they might use rouge, med, or bleu, but it's not enough. So this is really fundamental how we're evaluating. And that also helps us, and that's why I'm saying about the human evaluation, which is absolutely fundamental. Long time ago, people were talking about intrinsic and extrinsic evaluation. And when I was talking about the extrinsic, the humans, it was sort of neglected. People were always thinking that the intrinsic is more important. I'm so pleased now the time has come with the big models, pre-trained language models, to understand that the human aspect is actually important. So I think because we need, and those are one of the challenges, is that I didn't have the time to talk. What are the basically public data sets that allow us to evaluate? And that is, currently they're very imbalanced, okay? We have very limited, especially specific areas. If we take electronic health records, they're very limited. So if we want to talk about different metrics, we need to have more publicly available data sets which are actually produced by humans. Okay, that's one part. We have for domain specific, and that's a challenging thing because for domain specific areas, there is more sparsity of these data sets. So we need more of that. So those are the kind of availability of open data sets, which is a must, and how we develop them. Obviously, there are techniques as well to avoid labeled data. But if you talk about specific like biomedicine and so clinical data, we need to have more of that. And also to, as I said, to understand the factual correctness of what we produce. So we need the evaluations, different metrics and users in the loop.
Thank you for that response.
I was going to also ask you about the mentoring. You mentioned through your talk about some of the students that you've worked with, or that you've guided in this work, and I'm wondering if you have any special mechanisms or tips that you use when you're mentoring your students that we could learn from as well.
Well, first of all, I have to say that I've been blessed to have outstanding students. I just single out a few, but there were been, and also since it's women in AI, I have to say I'm quite proud that 50% or more of my lab are women in a computer science environment. I think that's a cool thing to have. Well, obviously, and actually outstanding students, both men and women, actually. It's very difficult to distinguish, but we have a very good representation. So the mentoring is when the student starts a PhD, although we have an initial, very, how do I say it, very close face-to-face type of relationship to, formulate the research idea. Then in my lab, I have many people we work as a team. So there is a lot of teamwork. And the mentoring is people taking responsibility in working in different projects they wish to do. So there are, students who are towards the end of the PhD also working with junior people, or if they think that the project is of interest to them, and I think they can benefit from using the data sets, or the problem is within their interests, then I put them together to work together. So they have also the benefit of increasing their, publications and the citations because they work with real data, but also ownership of their work. It's not just a lonely PhD, is a kind of their own work, but their own work embedded in other projects, in real projects. Just to give you an example, when we started working on systematic reviews, which is important for evidence-based medicine, there was a project that had funding for one postdoc. Well, my students showed a big interest in that area, and all of them were working as part of the thesis as well to do small parts and components and gaining a kind of contributing to the success of a project. This was important for the thesis. This was important for their publications because we had several publications where they had part ownership. I think teamwork is extremely important. Otherwise, a PhD can be a very lonely business. So at least it works in our lab.
Yeah.
So I guess.
Go ahead, Aisha.
Go ahead. Yeah. So touching on that, and I recall being in the research field as well, and certainly it is challenging sometimes, and also hard finding what your leadership style and also your career moves and pivots. How have you sort of navigated as a woman, just embracing within this field? It's impressive to hear that more than half of your lab are women, which is very, very unique. Just curious about sort of your leadership style and what you give to women who are looking to enter this field as just words of advice.
Well, I think when I started, it was a long time ago. I have to say it was not easy. Very often in my first job, I was the only woman in a university and in a department that you know, I felt that, to be honest, I didn't belong at all. So, and as women who are my age, a bit older, they would recall, it was extremely difficult to be taken into, you knew that people were not taking you seriously. And as a result, you know, I was very shy and I would never ask a question because I thought that whatever I was going to say, people thought I was stupid. And this is something that many women go through, hopefully not so much now, but I mean, a long time ago, in the 80s and 90s, I think I don't remember myself raising my hand to ask any question because I thought, you know, it wouldn't work. And obviously, most of the men were asking the questions, and most of the men were going forward. But at some point, and I guess after close to my 50s, I don't say anything else to the women to feel they have to reach 50 to be more confident. Then I realized that I had a voice. And I realized that I had lots of things to say, and I was realizing that I had many ideas, actually, which I thought, and then people who were saying, you know, you say, oh, great, John, or something, oh, great, this is a fantastic idea. I could have said that, but I was shy, I didn't. And I started realizing on my own the missed opportunities of doing things because I was not confident. It's very simple. Women are not confident, not that they're not confident. If you're in all male environment, you really stick out. So those are of course, not anymore. And one of the first things I thought I should be doing is when I created my team is to really promote. I saw a difference of quite a few women were applying to do a PhD for me. And then I realized that women, obviously, they want to work with another woman. And it was, I was becoming a role model in my team without realizing it. And that actually led to having several women as a PhD and postdocs I don't make any difference between male and female. All my students are fantastic. But it is very important to give a voice and to say to women that, well, don't give up. I mean, recently I said in my university, we celebrated Women's Day, and they say, what is your final saying? And I said, don't give up. Your voice is as valid as anybody else's. So you need to say what you think and not to give up. And even if people, you think that people don't take you seriously, you just continue, persevere. And in my case, because I started when things that were not so, women in computer science were about 5% or less. It took me some time, but I didn't give up. I think people, you need to express what you're thinking. Things are getting better, but not the way it should be. They should have been. I think we're really lagging behind, even in our advanced, supposedly more, open societies. Women are underrepresented. There are not many women professors in computer science, which is about, 10%. Although there are many female students. So we have lots of disparities.
Right, and I think, one of the things, listening to your research, it's so important that everyone is represented in doing this work, because this is going to impact all of us, especially as
indeed. And also something I didn't have the chance to say, because it's another topic. It's about, we worked on gender and pre-trained language models, because there is a bias in the pre-trained language models towards a specific type of population. And they're mostly men, and they're men of a specific type, men. So minorities, ethnic minorities, and women and other minorities are not represented. So there are lots of dangers in those pre-trained language models. And one has to be, of course, people have worked on creating models and putting a gender balance in those techniques. For instance, if you're working on emotion detection, you're talking about the models which are trained based on men of specific countries. So, and they're not even culturally adapted. That's another issue as well. So when we're talking about emotion in a different country, it's a different thing altogether in a different part of the world. So there are lots of unbalances and biases in our field, and the pre-trained language, language models, there was a danger, the different dangers there we should be aware of.
And Angelica in the chat has said that she's a PhD candidate and at 50 years old, she has lived everything you've mentioned. Sometimes it feels very lonely among men, and congratulate you on your wonderful work. And Angelica, would you like to join in the conversation, or are you comfortable just with the chat? Counting to 3. When I used to work at IBM after I finished my PhD, before I joined the University of Toronto, and I had the privilege of listening to Ginny Rometty, who went on to become the CEO of IBM, but at the time she was in charge of IBM's service business. And I at a women in computing event, and she was talking about how she struggled at the time with stepping out of her comfort zone when offered opportunities, and how she encouraged all of us to step out of our comfort zone. And I think that's what you're talking about, right? Is not to be afraid of putting
yeah, you need to have, I think it's very important to have the role models. It's very important for your mentors. And I mean, I do promote not only women, but I have to promote. You need somebody senior to promote the junior people. And when we're in meetings, I don't do the talking, and I say, well, X can do that. Or she can give a better answer than me, which is actually true because they're doing the research in depth. So it's very important to empower the younger people because they're super smart and they have to believe in themselves. And it's up to the senior people, the mentors, to give this to them. So that's fundamental. You need to offer the ability to your students, the junior staff, to shine, basically. And if the mentors don't do that, well, they're not good mentors, I think. Sorry, that's how it is.
Okay, Aisha, last word to you, and then I'll close. But I just want to say that was a pretty good thing to end on.
It was very good, and I'm sorry to kind of follow with this, but what do you see as the future of all of the different technologies that we see coming forward, and also for opening up for people who may not have a voice within this sector and are trying to look to really kind of expand their voice and make sure that they're heard?
That's a difficult one about how to make people, because this has to do with engagement and how different universities or different places or companies, because currently there are many dangers. So there is all this is geared by big IT companies. And when we're talking about PLMs and all that, what I didn't say is about the cost of developing all those models, and how even when we try to train our models, even in the UK, it's so expensive. So how can people from other countries, which are not so affluent and lucky as us, to have access to resources? So that is a different discussion. It's a long discussion. And that worries me a lot, that we become very exclusive about people who are basically rich in doing this type of work. And we really exclude people who don't have the resources. So obviously the future, it's a long discussion. Maybe I can discuss that in the second part. But I'm concerned about the inequalities that this technology introduces to our society. And I don't think this is for all. I think the impact is huge in our everyday life, but not everybody is part of this development. This is for the very few, and it's quite polarized. So we need to think how we can democratize these big models. So there are ways how not only democratize, but how can we make them greener? Because, developing this mega like ChatGPT and all that, what does it talk about for the environment developing these models? The computational costs are environmental costs. So there are many aspects as well, and they're also expensive. So those are aspects we have to consider about how we can democratize our research for everyone.
I think that is a perfect ending to a perfect day or a perfect event. This is a global series, and so that's a challenge that we should take to make sure that we're being as inclusive as possible, and also that we must continue to mentor one another, which is another goal of this series. So thank you again, Sophia, for an extremely engaging presentation.
Thank you for having me. It was great talking to you.
Thank you. So as we leave, we'll be prompted to answer a short survey. So thank you for doing that. Please submit your feedback, and I thank you for that in advance. Our next session is on April 18th with Maren Benowitz, a professor of robotics at the University of Bonn, who will explore her work utilizing convolution neural networks and reinforcement learning to enable service robots to act with foresight when navigating human environments. For details of that event and all other things, please check out the Schwartz Reisman Institute website. Follow us on Twitter and our mailing list, and those will be in the Zoom links or Zoom chat as you leave. And I want to say thanks again and look forward to seeing you all soon.